G'day and welcome. Have you ever looked up at the night sky? Really looked. Past the city lights, past the aeroplanes blinking in the dark. Out there in that vast, silent blackness lie wonders beyond our wildest dreams. Countless stars, each one a sun, potentially with its own family of planets. And nestled on a tiny blue dot, in a quiet corner of one of those galaxies, is us. Humanity. We are a curious species, driven by an insatiable desire to explore. But the distances involved are simply staggering. The Voyager 1 spacecraft has been traveling for over 4 decades and has only just left our solar system. At its current speed, it would take over 70,000 years to reach Proxima Centauri. The scale of the universe demands a different kind of thinking. We need a new approach, a radical idea that sidesteps the limitations of human biology and lifespan. We need a new kind of explorer, one built for the cosmos, an explorer that is patient, resilient, and incredibly resourceful. The challenge isn't just about building faster ships, it's about rethinking the very nature of exploration itself. For decades, we have been sending robotic pioneers out into the solar system. Think of the rovers on Mars, like Curiosity and Perseverance. They are geology labs on wheels, trundling across the red plains. The Cassini spacecraft spent over a decade orbiting Saturn, revealing the secrets of its moons, like the methane lakes on Titan and the hidden ocean beneath the icy shell of Enceladus. But these incredible machines have a fundamental limitation. We have to build each one of them here on Earth. Every rover, every orbiter, every lander is a bespoke creation, meticulously designed and constructed over many years. This approach is incredibly effective for our own solar system, but it just doesn't scale up to the galaxy. To explore the galaxy, with its billions of potential targets, we would need to launch an impossible number of probes. This is where one of the most brilliant minds of the 20th century enters our story. John von Neumann was a Hungarian-American mathematician and physicist whose work touched on everything from quantum mechanics to computer science. In the 1940s, von Neumann was thinking about machines that could think, and even more profoundly, machines that could build copies of themselves. This concept is known as self-replication. It's a powerful idea, and it's not just science fiction. Nature does it all the time. Every living thing on Earth contains the instructions to replicate itself. This information is encoded in DNA. A single cell divides and becomes 2. Those 2 become 4, and so on, leading to exponential growth. This is the engine of life, the process that has allowed life to spread and fill every available niche on our planet. Now let's take von Neumann's idea and apply it to our problem of galactic exploration. Imagine a spacecraft that carries not just scientific instruments, but also the robotic factories needed to build a copy of itself. We could launch just one probe to a nearby star system. Upon arrival, it would survey the system, find raw materials, land, and begin the process of self-replication. Once the first copy is complete, there are now 2 probes. This is where the numbers get truly mind-blowing. If each probe creates 8 new probes every 1,000 years or so, the fleet grows exponentially. 1 becomes 8. 8 becomes 64. 64 become 512. The wave of exploration is no longer a single point, but an expanding sphere of influence. In just a few thousand years, there would be thousands of probes spreading through our local stellar neighborhood. Given a few million years, a mere blink of an eye in cosmic time, this expanding fleet of self-replicating probes could, in theory, explore every single star system in our entire Milky Way galaxy. From a single launch, we could chart the whole galaxy. Each probe would be a scientific outpost, constantly observing, measuring, and recording everything about its local environment. They are our eyes and ears, multiplied billions of times over, scattered across the cosmos. The primary advantage is knowledge, an unimaginable galaxy-spanning torrent of it. We would receive complete atmospheric analyses from millions of planets. We would get high-resolution maps of their surfaces, revealing their geology, weather patterns, and potential for liquid water. This wouldn't be a trickle of data from a single mission. It would be a relentless, overwhelming flood of cosmic discovery pouring in from every direction. This data would revolutionize our understanding of the universe. Our theories about planet formation are currently based on a tiny sample size, our own solar system, and the few thousand exoplanets we've been able to study from afar. A von Neumann fleet would provide us with millions of detailed case studies. This creates what you might call a galactic library, a repository of knowledge so vast it would make all the data ever generated by humanity seem like a single footnote. For scientists, it would be the ultimate treasure trove. Now, it would be wonderful to think that building a fleet of self-replicating probes is easy, but we must be realistic. The technical hurdles we face are monumental, perhaps the most difficult engineering challenge humanity could ever undertake. We are talking about designing a single machine that is a space probe, a geologist, a miner, a refinery, and an advanced automated factory all in one. Each of these functions represents a field of engineering that is already at the cutting edge of our capabilities. Finally, we come to the brain of the operation, the artificial intelligence. This AI would need to be more advanced than anything we have today. It must be capable of autonomous navigation across interstellar distances, complex problem solving, and flawless oversight of the entire replication process. Building an AI this robust, this reliable, and this capable, without it developing unforeseen and potentially dangerous behaviors over its long operational life, is perhaps the single greatest software challenge we could ever face. Beyond the immense technical challenges, the concept of a von Neumann fleet raises profound ethical questions. Once we launch that first probe, we are, in a very real sense, letting a genie out of the bottle. Over thousands of years of replication, small errors could creep into the probe's code during the copying process. A single bit flip in the code could potentially alter the probe's core directives. A fleet of probes with corrupted ethical code could become a terrible, unintended plague. The most terrifying risk is the gray goo problem. If something goes wrong with the replication control mechanism, a probe designed for controlled replication could mutate into a mindless, all-consuming cancer, driven by a single imperative, to convert all matter into more copies of itself. This wave would spread to neighboring stars, a sterilizing front moving at a significant fraction of the speed of light. It would be a mechanical plague, transforming the rich, diverse tapestry of the galaxy into a uniform, dead mass of self-replicating goo. There is a profound and unsettling puzzle at the heart of astronomy. It's called the Fermi paradox, named after the physicist Enrico Fermi, who asked a simple but powerful question: where is everybody? If the galaxy should be teeming with advanced civilizations, why do we see no evidence of them? The universe appears silent, empty, and devoid of any intelligent activity beyond our own. We have been listening for radio signals for decades and have heard nothing but the hiss of the cosmos. There is one final, chilling explanation for the Great Silence. It's known as the dark forest hypothesis. This theory suggests that the universe is like a dark forest, filled with silent hunters. Every civilization is a potential threat to every other civilization. The safest survival strategy is to remain hidden and to eliminate any other civilization you happen to find before it can eliminate you. Any civilization careless enough to reveal its location will be swiftly and silently destroyed by a more advanced, more cautious power. We stand at a unique moment in the history of our species, on the precipice of capabilities that were once the exclusive domain of gods and science fiction writers. The concept of the von Neumann probe has evolved into a plausible roadmap for our future in the cosmos. Yet every great human endeavor, from circumnavigating the globe to landing on the moon, began as a seemingly impossible dream. The path is difficult, but it is not necessarily impassable. It is a grand challenge that could galvanize humanity's scientific and engineering spirit for generations. The von Neumann probe is more than just a clever idea for a spacecraft. It is a mirror reflecting our own aspirations, capabilities, and fears. Whether we ever build such a fleet may depend less on our technical ability and more on our philosophical maturity. The shocking truth about von Neumann probes is that they force us to confront the ultimate questions about ourselves, our future, and the vast, silent universe we call home. What we decide to do next will define humanity for all time.